Hi, my name is Daniel Blackburn, and in this video I will teach you how to use Excel to make standard deviations, average standard deviations, build bar charts expressing these deviation bars, and also to how to do ANOVA on your data to see if there is any statistically significant difference between the treatments that you have. So this will be useful and required for you to express correctly the data in your lab reports from the SWAE4401 virtual practicals. So stick with us and let's see if you learned something new. All right, so for many of you, if you already know how to do this, this is absolutely fine if you jump this video. But for the ones that are not really sure or want to revise these basic concepts of using Excel, I will show you very quickly how to do this. And here you will see on the screen, this is my Excel screen, and you have two data sets. One is plant height in centimeters, and you have also plant dry weight in grams per plant, in grams per plant. This is a hypothetical result from an experiment. So you got here, you will have repetition 1, rep 1, rep 2, and rep 3. And what you will do with this data now, you will need to calculate average and standard deviation, average and standard deviation. So what you have to do here is insert a formula. Just press equal. You see here on the top, it will show the equal sign. Press equal and then write the formula average. And you see already the function already appearing in the Excel. So open brackets here, and then you have to select the range. To select the range, press the Shift key on your keyboard, click on the top, and then drag down up to the bottom, and then release. Then you selected the range where you want to take your average from. So close the brackets and press enter. Then you will see that the average from this is 33. Now if you see the on the bottom portion of the cell, if you put your mouse there, it will appear a black cross. When that appears, you click and you can drag your formula to the side. When you drag your formula to the side, and we now calculate considering the second treatment, the replications for the second treatment. So here on the top will be the average. Here will be the average for the treatment with soil organic matter, and here 27.6 will be the average for the treatment without soil organic matter. So for the standard deviation, we will do similarly the same thing. Now you're going to put equal, and you're going to write STDEV, STDEV, open brackets, select the range similarly, and close the brackets, press enter. So you will say standard deviation is a measurement of how distributed are your data around your average. So it's kind of 33 plus minus 3. Plus minus 3. So I will just reduce here the number of decimal cases. Okay. So it's not so confusing. I will also drag this down to not mix the data with the replicates. And we can do again, drag the formula from the standard deviation towards the side when it appears black um, the black cross. Yeah? I will also reduce here the amount of decimal places, significant cases that you have. And oh, this is something, let's do here 39. Yeah? This was some mistake that I had before. So it will be here that one treatment will be 33 plus or minus 3, and the other treatment will be 37.7 plus minus 1.5. So you can already see that the difference are quite high between these two treatments, and most likely there's a high significance. But we can calculate actually what is the probability of this treatment being different from the other one. Before we move to that, let's just calculate the same thing for the next data set. Whenever you have these formulas dragging, you can also drag them by copy pasting them. So you can select this range, and if you press Ctrl C, it's copying, Ctrl C, and then again Ctrl V, paste. Yeah, so you will do that. You will see that this again, this will be already calculated the average and standard deviation for the next data set. Yeah, for the next data set for plant dry weight, you have the average of one treatment would be 2.27 plus minus 0.21. The other one will be 2.40 plus minus 0.10. And so this is a little bit more dodgy, so you don't know exactly if these are different or not. We need to now check if they are really statistically different or not. Okay, statistically different or not. But before we do that, I will now show you how to make a bar chart of this data. Okay, so you will here on the top insert, and this icon here of bar chart, and you will select the first one. Okay, so let's decrease the size of this bar chart so we can have a clear look here on the wing on the. So you can actually manipulate some of the elements of this chart. The title, I recommend you not to use the title. You just add the description on the caption, yeah, and the caption of the chart. Now what you need to come here is, and then you right click on the graphic and go to select data. Yeah? Select data, and here the horizontal categories, you need to edit those. Yeah? Edit, and then you will, when you click and you say cancel again, edit, then in this right corner here, click on that and select what are the categories, with organic matter and without organic matter. Yeah? Okay. And then you're going to be marked here with soil organic matter, without soil organic matter on your chart. Okay? It will be marked already here. Next thing you want to do, you already have the labels for the treatments. Now you want to have the labels for the y-axis. Yeah? You will click here on the plus on the corner of the chart, and you click axis title. Yeah? And you can label here soil organic matter sum, and on the y-axis you need to add what is your response variable. Yeah, response variable, plant height in centimeters. So this is the appropriate way to label your axis. You put the name of the response variable, and you, in between brackets, you add the units. Yeah, always use the units. We want to know what are the units that you used. Next important thing that you need to add to this graphic is the dispersion bars. Yeah, so you need to go here on the plus here on the side, click here, and then you will go and error bars. Yeah, click on error bars. There's an automatic value that comes with these error bars, but you don't want to use those. You want to add your own. Yeah, so the error bars, you will click here on the arrow on the side, and you will click the option more options, and in the more options, no, it's not here, error bars, more options here. This is actually the menu for more options, and you're gonna go to the side here, and you're gonna click custom. Yeah, custom. It's behind my image here, so I will maybe move to the side a little bit. Custom, and you put a specify value, and you will get off the way, specify value. When you specify value, it will give the positive range and the negative range. So you want to click here on the side and select the standard deviation for the positive, and you will select the standard deviation for the negative. Yeah, it means that now the dispersion bars that are showing on your chart are exactly the ones that are regarding the standard deviation from the data that you have. Yeah, this is dispersion of the data. The bigger these bars are, it means that the data are more less precise. They are varying more. And the smaller these bars are, it means this data is more precise. You can trust it more. Okay. Now, how much can you trust it? What is the probability of these two treatments being different from each other? Now, what you have to do to evaluate what is this probability, you need to do an analysis of variance, So you will come here to data, select data analysis, and in data analysis, you will select ANOVA single factor. Single factor. Press OK. Then you're gonna say the input range, which is your data. Yeah, your input range will be your data. You will say that you are working with, maybe even let's include the labels. Yeah, with soil organic matter, without soil organic matter. Labels in the first row by columns. Yeah, labels in the first row. The alpha of 0.05. Okay. And output range I will put on the same worksheet. Yeah, output range I will put in the same worksheet, and I will mark just here below this. Yeah, output range on the same worksheet. Okay, and then here you got it. This is the result. Yeah, ANOVA single factor. You got the summary of this, but I recommend you to go. This will go the counts, the sum, the average, the variance. But what you have to look is for the p-value. Yeah, p-value, it's here. Yeah, here is your p-value. Yeah. P-value. This is what you have. The p-value is the probability that these results are different from each other or not. So you have actually 7% probability of having this result is not really different. Yeah. The better way of interpreting the p-value is how many times you have to repeat your experiment to have one false positive. Yeah. So if you divide one by this p-value, it gives you a number. It means that you have, if you repeat your experiment 13 times with this same deviation, one of the 13 times you will get that this will be a false, it will say that it is not different when it really is different, okay? So this is the threshold, you know, it gives you the probability, the how many times you have to repeat your experiment in order to get one false positive here. So actually, when the p-value is below 0.05 is when we consider in science that this is a significant difference. If the p-value is not below 0.05, then we say it's not significant. And then when the p-value is below 0.01, then we say that it's highly significant. Yeah, it's highly significant, the statistical difference. So you can do the same thing for the other data set, and it will give you the p-value that you will find for this. Okay. When you have significant differences, then you come here and you can add an asterisk to this figure when you have differences. And the asterisk will denote that the differences, the probability that this is really accurately different from each other is below 0.05. 0.05 means that you will get a false result every 20 times you repeat that experiment. So it's a good standard. And the probability of 0.01, it means that you have to repeat the experiment 100 times to get one false result. Yeah, you will get the result that is not telling the truth. Yeah, so just by chance. So this p-value is telling you how likely it is that your values are really different from each other or not. Yeah? If this range of variation decreases, let's say if you had here, instead of 36, you have 34, you know, or 33, or 30, let's put 34, and this 30, let's say it was 32. It means now that the standard deviation is smaller, and this ANOVA will be more precise, will tell you that the probability is lower. The probability of being false is lower. If you just come here and let's do the ANOVA again, now having lower variation, data analysis, ANOVA single factor, the same thing, yeah, same range of data, and same output labels, okay, same, all the same. And now the results will give us that our p-value is 0.01, yeah? And now it means that, what means the p-value of 0.011 is that we have to repeat, if we repeated the experiment 87 times, this, we will get once that it will be by chance that the results will tell the wrong information. So now if it's like this, then this will be significant. So we can come here and add data labels, yeah, add data labels on the figure. And we delete here, and we can, or just put here an asterisk that the effect is of soil organic matter is significant. Yeah, you add an asterisk to this. It means that it's significant. Yeah? Statistically significant. If it was below 0.01, then we put here 2 asterisks. Yeah? It means it's highly significant. So this is the way that you have to show your data on your in your reports. Yeah, I want you to show bar charts with your response parameters, and you have to show them with dispersion bars, and you please check if they are statistically different from each other or not, okay, by comparing them using analysis of variance. Okay, I hope that this is useful for you. If not, it's good that you already have this knowledge. But otherwise, if you don't, this is instructions of how to do this analysis. Thank you very much.